Welcome to AI Frontiers, where advancements in artificial intelligence are explored. Today's focus is on the cutting-edge field of computer vision. This discipline enables machines to interpret and understand visual information from the world, forming a cornerstone of modern AI research. Innovations discussed today include machine perception, continual learning, generative modeling, and anomaly detection. These breakthroughs bridge raw visual data with actionable insights, driving technological progress. Published on May 17, 2025, the highlighted research pushes the boundaries of what machines can see and learn. By the end of this episode, a comprehensive understanding of the progress made, remaining challenges, and promising directions in computer vision will be provided. Computer vision focuses on enabling machines to interpret and understand visual information, much like humans. Consider systems capable of recognizing objects and images, detecting anomalies in hyperspectral data, or generating realistic synthetic videos. This encapsulates the essence of computer vision. The significance of this field lies in transforming raw visual data into meaningful insights across diverse applications. For example, hyperspectral imaging captures information across many wavelengths, revealing details invisible to the human eye. This technique has revolutionized agriculture, environmental monitoring, and defense by detecting subtle changes in crops, identifying mineral deposits, or spotting contaminants. Another exciting area is generative modeling, where diffusion models create synthetic images or videos, reshaping creative industries and enhancing entertainment experiences. The papers discussed today exemplify these advancements, showcasing how researchers tackle challenges like continual learning, anomaly detection, and semantic segmentation. Together they demonstrate the breadth and depth of innovation in computer vision, highlighting its potential to solve real-world problems and drive technological progress. A key theme emerging from recent research is continual learning, addressing the challenge of training models to acquire new knowledge without forgetting previously learned tasks. Jianing Wang and colleagues introduced two frameworks, CL-BioGAN and CL-CADAN, specifically designed for hyperspectral anomaly detection. These methods draw inspiration from biological neural networks, emphasizing adaptability in cross-domain scenarios. CL-BioGAN introduces biologically inspired loss functions for stability and flexibility, while CL-CADAN integrates capsule networks to retain discriminative learning across domains. Both frameworks address catastrophic forgetting in dynamic environments, ensuring models remain effective as they encounter new data. These innovations highlight the ongoing efforts to make AI systems more adaptable and reliable over time. Another prominent theme is generative modeling, particularly through diffusion models. Fuying Wang and team explored negative preference optimization, a novel approach to training models to avoid undesirable outputs while aligning with human preferences. This work underscores the growing need for fine-grained control over AI-generated content. Self-NPO aligns generative outputs with human preferences, eliminating costly preference annotations and enhancing scalability. By enabling fine-grained control over undesirable outputs in diffusion models, this method ensures that AI-generated content meets both technical and societal standards. Such advancements pave the way for more reliable and user-aligned generative systems. A third recurring theme is anomaly detection, especially in hyperspectral imagery. Both CL-BioGAN and CL-CADAN excel in hyperspectral anomaly detection, leveraging GANs and capsule networks for precise localization. Detecting rare but significant events, such as oil spills, crop diseases, and contaminants, is critical in fields like remote sensing. These frameworks provide robust tools for spotting anomalies that could have severe consequences if left undetected. By combining advanced techniques like GANs and capsule networks, researchers are enhancing the precision and reliability of anomaly detection systems, contributing to safer and more informed decision-making in various industries. Among the groundbreaking findings, Jianing Wang and colleagues' CL-BioGAN achieves robust performance with fewer parameters, addressing catastrophic forgetting while providing new insights into neural adaptation mechanisms. Their CL-CADAN framework mitigates forgetting while retaining discriminative capabilities across different scenarios, representing a significant step forward in cross-domain hyperspectral anomaly detection. Additionally, Fuying Wang and colleagues' Self-NPO ensures high-quality, human-aligned generative outputs by eliminating the need for explicit preference annotations. These contributions collectively underscore rapid progress in addressing real-world challenges like limited prior information, computational constraints, and the need for human-aligned AI systems. The methodologies employed in these papers reflect a blend of established techniques and innovative adaptations, each with strengths and trade-offs. Generative adversarial networks, or GANs, are widely used to model background distributions and detect anomalies in hyperspectral imagery. While GANs excel at generating realistic data, they face issues like mode collapse and training instability. Self-attention mechanisms allow models to focus on the most relevant parts of an input, improving detection accuracy, but increasing computational costs. Capsule networks encode spatial hierarchies and relationships between features, making them well-suited for tasks requiring precise localization. However, they often require significant computational resources and careful tuning. Photometric distortion augmentation simulates diverse lighting conditions, improving generalization in semantic segmentation tasks. Negative preference optimization exemplifies a novel application of classifier-free guidance, ensuring greater alignment with human preferences, while requiring careful balancing to prevent overcorrection. Each methodology brings unique strengths and trade-offs, reflecting the complexity and creativity inherent in modern computer vision research. Jianing Wang and colleagues CL Biogan addresses the challenge of continual learning in hyperspectral anomaly detection, where models must adapt to new domains without forgetting previously learned knowledge. The authors propose a biologically inspired framework incorporating active forgetting and replay strategies to balance memory stability and learning flexibility. At the heart of CL Biogan is the continual learning bio-inspired loss, combining an active forgetting loss and a continual learning loss to regulate parameter updates from a Bayesian perspective. This innovative approach allows the model to release outdated knowledge while retaining essential information for new tasks. The integration of self-attention mechanisms enhances the model's ability to fit background distributions, critical for open scenario anomaly detection. Experimental results demonstrate that CL Biogan achieves superior accuracy with fewer parameters and lower computational costs compared to existing methods. This dual contribution advances the field of continual learning and provides valuable insights into neural adaptation mechanisms, paving the way for more robust and adaptable AI systems. Jianing Wang and colleagues CL Kagan is a capsule-based generative adversarial network designed for cross-domain hyperspectral anomaly detection. The framework leverages a modified capsule structure with adversarial learning to estimate background distributions, overcoming the limitations of prior information scarcity. To mitigate catastrophic forgetting, clustering-based sample replay strategies and self-distillation regularization ensure retention of discriminative learning abilities across different scenarios. A key innovation in CL Kagan is the incorporation of differentiable enhancement, which stabilizes the training process and improves convergence. This enhancement boosts generation performance of training data and strengthens reconstruction of background samples. Through rigorous experimentation on real hyperspectral datasets, the authors demonstrate that CL Kagan outperforms existing methods in terms of detection accuracy and continual learning capacity, marking a significant advancement in addressing cross-domain anomaly detection challenges. Fuyan Wang and colleagues' Self-NPO tackles the problem of aligning generative models with human preferences through negative preference optimization. Unlike previous approaches relying on costly and fragile procedures for obtaining explicit preference annotations, Self-NPO learns exclusively from the model itself, eliminating manual labeling or reward model training. This makes the method highly scalable and practical. Self-NPO seamlessly integrates with popular diffusion models, including SD 1.5, SDXL, and CogVideo-X, consistently improving both generation quality and alignment with human preferences. Importantly, this method does not require exhaustive data sampling, further enhancing its efficiency. By addressing a critical gap in preference optimization, Self-NPO opens new possibilities for fine-grained control over AI-generated content, ensuring models produce outputs that are visually appealing and aligned with societal values. Several promising directions emerge from recent advancements in computer vision. One clear trend is the movement towards more sophisticated and targeted architectural innovations, as evidenced by the success of orthogonal residual updates and biologically inspired frameworks. Researchers seek fundamental changes to how networks learn and represent information. This pursuit is complemented by growing emphasis on multimodal approaches, combining different types of data and reasoning capabilities to solve complex problems. For instance, integrating vision and language models for medical image segmentation demonstrates the potential of multimodal systems to provide richer contextual understanding. Another important direction is focusing on practical deployment considerations, including safety evaluation and robustness against uncertain inputs. Papers addressing video-based attacks and uncertainty quantification highlight the need for continued research in making AI systems more reliable and trustworthy in real-world applications. However, challenges like computational inefficiency, data scarcity, and the need for human-aligned AI systems persist, requiring collaboration between researchers, practitioners, and domain experts to ensure technological advances translate into meaningful improvements across various application areas. This presentation was synthesized using advanced tools including GPT, QuenQuen Max, TTS via DeepGram, and image generation via Grok. Human review ensured accuracy, though potential oversights are acknowledged. References are provided for all cited works, ensuring transparency and credibility. The synthesis process combines state-of-the-art AI technologies to create a cohesive and informative overview of recent advancements in computer vision. This approach highlights the collaborative potential of human expertise and AI-driven tools in advancing scientific communication and understanding. Thank you for joining us on this exploration of the frontiers of computer vision. Subscribe to AI Frontiers on YouTube for more insights into cutting-edge research. Stay updated on the latest advancements in artificial intelligence as we continue exploring transformative technologies shaping our future.